The IMLOG2 function within Excel allows us to perform a base 2 logarithm on a complex number. A complex number consists out of a real part and an imaginary part. That's also where the abbreviation of the IM and the IMLOG2 function comes from this imaginary part of the complex number. Now, a complex number we can represent on the complex plane, where the x-axis represents the real part of the number and the y-axis represents the imaginary part of the complex number. Now, in essence, using the IMLOG2 function is quite straightforward. As you can see, I have a list of complex numbers, some of which have a real part, an imaginary part, or a combination of both. So we start by writing IMLOG2, opening the parentheses, and we only need to supply one argument, being an I number or being a complex number. So you can see I have a list of complex numbers. I select this number, I close the parentheses, and I pull this down, and I get the result of the base 2 logarithm of the respective complex number. Now, it is important to understand that complex numbers within Excel are represented as strings and not actual numbers. So you can do easy calculations with them. You first need to convert them back to decimal numbers, and then you can do your computations with them. Now, here we have the result. What you can see is that we cannot perform a base 2 logarithm of the number 0, but every other possibility works just fine. To better understand how the IMLOG2 function works in Excel, we will take steps to reconstruct the result of this function. Now, the first thing we need to do is to separate the real and the imaginary part of our complex number. Because in Excel, a complex number is really just represented as a string, and we cannot do any easy calculations with this. So in column C here, we will be calculating the real part. And so we can do this using the function mReal, which will return the real coefficient of a complex number. It only takes in one argument, just like the IMLOG2 function. It is the complex number. I press enter and I pull this downwards. And so what this gives us is the real part of the complex number. So this is each time 2 here, 1 over here, 0 down, and then -1 and -2. Now we can do the same thing to extract the imaginary part or the imaginary coefficient of the complex number, which we do with the imaginary function. So this will return the imaginary coefficient of a complex number. So we supply that as the argument and pull this downwards. And so you can see each time it goes from 2 to -2 because those are the complex numbers I've chosen. Now, the current form you see of this complex number is the rectangle form, meaning we supply the number of units we have to go to the right on the real axis of the complex number, and then the number of units we need to go up or down on the imaginary axis of the complex plane. Now, there is a different way to represent a complex number, and that could either be through the polar form or through the exponential form. And so the exponential form is what we are looking to obtain, because that's easier to take a logarithm of. Now, the exponential form of a complex number is r times e to the power theta I, where e, of course, represents Euler's number, which is 2.7, 18, 28, etc. And so then we only need to calculate two numbers here, which are r and theta. Now, r represents the distance from the center up until the point. So we calculate the distance from 0, 0 to the point we are looking at. A complex number is represented on the complex plane, where the x-axis represents the real number and the y-axis represents the imaginary part. So we take the real part, do this to the power of 2, and we add to this the imaginary part to the power of 2, and then take the square root of this. This simply is using the Pythagorean theorem to calculate a distance between 2 points. So let's do that first. So we are going to take the square root. We can do this using the SQRT function. And so we need to supply one number, and this number is calculated by taking the real part to the power 2 and add to this the imaginary part to the power 2. As such, I close the parentheses, press enter, and we can pull this down. So now we have found the distance of the point 0, 0 to our complex number. Now we know the distance, but we also must know the angle at which to take this distance. This angle is represented by the Greek letter theta. So to find this angle theta, we need to take the arctangents of our number. So how we do this is we use the a tan2 function within Excel, which will return the arctangent of a specified x and y coordinates, and the result will be in radians. Now, first we need to supply the x number, and just like I mentioned earlier, the real number, we put that on the x-axis of our complex plane. So I put the real number as the first argument, and then I put the imaginary part as the y number. I close the parentheses, press enter, and pull this down. So there we have found the angle theta that we get by plotting the complex number on the complex plane. And so each number is specifically identified by the distance from the center and the angle we take from the x-axis. Now, one thing that is quite interesting here is that if we take the number -1, you can see that when we calculate the arctangents of that, we are getting 3.1415, so in essence this is pi, which we can find at 180 degrees on our unit circle. You can also see that we get pi divided by 2 when our complex number only consists out of an imaginary part, so the complex number is then positioned on the y-axis, which contains the imaginary part of our complex number. Okay, so now that we have found the two variables that we needed to convert our complex number from the rectangular form to the exponential form, we can construct the exponential form. Okay, so we write this as following. We take the r, which was the distance from 0, 0 to our point. Now I will round this down to make it a little bit more neater, so we can use the round function for this and then specify the number of digits we want to round this to. So I'll take 2. And then we add to this, and for this I use an ampersand to concatenate strings, the rest. So that would be e, which is Euler's number, to the power, and then I wrap this in parentheses, of theta, which I will also be rounding down to 2 digits. And then I add to this I and close the parentheses as well, as such. So there we have the exponential form. Now, of course, it's not exact because I used that rounding, but it gives an idea of what you can expect. Now, I needed to use ampersands and double quotation marks to merge these strings together because, like I mentioned earlier, complex numbers are not considered actual numbers in Excel, they are considered strings. So that's why we need to do it like this. Okay, so now that we have our complex number and the exponential form, it will now be easier to take a logarithm of that number. Now, for this, we will use the natural logarithm, which is the ln. So we want to take the natural logarithm of the complex number in exponential form. Now, this would look like this. Now, fortunately, due to the rules of logarithms, if we multiply parts of a logarithm, we can actually separate them and add them together afterwards. So we can first take the natural logarithm of r, and then take the natural logarithm of e to the power theta I. Now, if we take a look here to the natural logarithm of e to the power of theta I, we can see that we are taking the natural logarithm to Euler's number to the power of something. Now, Euler's number and the natural logarithm cancel each other out. So that is also exactly the reason why we are taking the natural logarithm here. So we could simply write this as theta I. So here I will be writing, we will round theta to 2 digits, and then we add to it I. Okay, now I can pull this through. And so this is exactly the reason why we first wanted to convert our complex number into the exponential form, so that then the e cancels the natural logarithm out. Okay, so now all that's left to do is to take the natural logarithm of r. So I use the ln function for this, which will take the natural logarithm of a decimal real number. Now r was defined here by taking the distance from the point 0 up until the complex point. So I press enter and I pull this down. Okay, so now all we need to do is to add these parts together. So I will be rounding down the natural logarithm of r down to 2 digits. So I use the round function and I bring this to 2 digits. Then I concatenate a plus, and then I concatenate the theta I. There we go. I pull this down. And so this is now the natural logarithm of the complex number we had earlier. Now we can verify if this was correct, so I will insert a new column here. And so what we will be calculating here is the natural logarithm of the complex number, and for this there is a function in Excel which is called IMLN. We supply a complex number to it, and automatically the natural logarithm of that complex number will be calculated. And so as you can see, of course, given the roundings, the numbers match exactly. So far, so good. Now, we got the natural logarithm of our complex number. Now we need to take a logarithm of base 2, whereas the natural logarithm is a logarithm of base e. Now, fortunately, there is a calculation rule when working with logarithms, which also applies in the complex plane. And it says if we take a division of two logarithms, which each have the same base, then we can take the number we took the logarithm from in the denominator, and that would be the base of a new logarithm. It is what is written here in cell L2. If we want a base 2 logarithm of a complex number z, that equals to the natural logarithm of z divided by the natural logarithm of 2. So in order to calculate this, we will have to divide both the real and the imaginary part of the natural logarithm of our complex number by the value of the natural logarithm of 2. Then we add those two parts together, and then we have the result of a base 2 logarithm of a complex number. So let's start with the real part here. So to do this, we are going to take the real part, which we can find here in column I, where we took the natural logarithm of r, and remember r was the distance from the center up until the point. And so we will be dividing this by the natural logarithm, so ln2, to get the real part when performing a base 2 logarithmic operation on the complex number. So I press enter and I pull this down. Now we do the same thing for the imaginary part. Now remember, the natural logarithm of the imaginary part, well, that was where we had e to the power something, so the natural logarithm and Euler's number cancelled each others out. So what we really ended up with was simply theta. And so theta was the arctangent we took from the x-axis up until the point. So this is here in column G. And so we divide this by the natural logarithm, so ln of 2. And I press enter and I pull this down. Now all we have to do to end up with the base 2 logarithm of our complex number is to add these two parts together. Now the first thing I will be doing is to take the real part and round this down to 2 digits. So round the real part to 2 digits. And then I want to add to this, so I use an ampersand with a plus sign, the imaginary number, which I will also be rounding down to 2 digits. So I use the round function. I supply the imaginary part, I round it down to 2 digits, and then I add to this I, just like this. Okay, so now I pull this down. And so here you can see the result of a base 2 logarithm of a complex number. So I will insert a new column here. I'll go to the right a bit more. And I will once again use the IMLOG2 function within Excel, so IMLOG2, where we supply the complex number, which we can find all the way to the left. I press enter, I pull this down, and now we can check if we're actually getting the same results. So what we see here is 1.5 plus 1.13i, well, that seems to match. When we look here, 1.16 plus 0.67i also seems to match. So as you can see, this matches for everything, given of course the rounding I supplied. Now in essence, the IMLOG2 function allows us to quickly take a base 2 logarithm of a complex number. And so what's going on behind the scenes is that we are converting the rectangle form of our complex number to an exponential form by calculating the distance from the center to this point and also the angle that is taken from the x-axis, being the real axis, to this point, which we represent by the letter theta. Then we take the natural logarithm of this complex number in the exponential form, and then we convert this to a base 2 logarithm. And as you can see, the final result matches exactly. If you found this helpful, consider subscribing to the channel for more videos like these. You can also leave a tip using the PayPal link in the description. Thanks for stopping by. Feel free to watch this recommended video.